Okay, so now I want to deduce the relationship between pressure and speed, right? So now I want to deduce the relationship between pressure and speed. Okay, so our starting point, right? So consider a molecule, right? This gas molecule inside a container, a cubic container, right? So it's colliding, so it moves from this face, right, to this shaded face, and then collides with this shaded face and rebounds elastically, right? So it collides with this shaded face and collide and rebounds. So there's elastic collision, an elastic collision, right? So first of all, I want to deduce the change in momentum, right, as it rebounds with that face. So the change in momentum, right? Let me just write a statement, right? Okay. So the change in momentum, right? So the change in momentum of the molecule as it rebounds at the shaded face is equal to, if its mass is m, right, and its speed is c. So we know that the change in momentum will be mc minus, so the final momentum will be in the negative direction. So it's supposed to be minus mc, right? Since the final momentum is in the negative direction, so this gives us the mc plus mc, which is equal to 2mc, right? So that's the change in momentum as it rebounds on the shaded face, right? Okay, now we have the change in momentum. So if this molecule travels from here, then and then it rebounds, right? Let's say it rebounds and then goes back and then rebounds. So if it rebounds, goes back to this face and then rebounds again. So we want to find the timing, right? The distance, the time it covers between collisions, right? Let's say it collides with this face and then goes back here and then collides again with this face and then comes back and collides with the shaded face. So it collides with the shaded face twice. So I want to find the time between the collisions, right? So it's going to travel a distance of 2L with the speed c, moving with the speed c. So it travels a distance of 2L, right? So which means time between collisions, is equal to, so time is equal to what? It's distance over speed. So it's 2L over c. So that's the time between collisions. Okay. So now we want to find the force, right? So according to Newton's second law, so the force exerted on this face, right? According to Newton's second law, the 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 force is equal to the rate of change of momentum, right? So the force is equal to the rate of change of momentum. So according, right, to Newton's, so according to Newton's second law, right? So according to Newton's second law of motion, right? So the force is equal to the rate of change of momentum, meaning F is equal to, the change of momentum is 2mc, right, over the time. So it's 2L over c, right? So which means the c goes there. So which means the F is equal to mc squared over L. So that's the force exerted on the shaded face, right? So that's the force exerted on this shaded face. Okay, so now I want to determine the pressure. What would be the pressure exerted? So we know that pressure is equal to force over area, right? So what is the force exerted? So the force exerted is mc squared, right, over L, right? So divided by the area of this shaded face it's a square area, so it's L squared, right? So it's L squared, meaning we have the pressure is equal to, so the pressure becomes mc squared over L cubed. So it's mc squared over L cubed, right? So that's the pressure, right? So we're considering one molecule, right? But there will be a large number of molecules in this container. We have a large number of molecules, right? So the number of molecules will be representing N, right? So this becomes P is equal to N representing the number. So Nm C squared over L cubed, right? Okay. So now we are here. So this molecule, there will be many molecules, right, moving in random directions. So in three planes, the XYZ plane, right, colliding with each other with the face of the container. So they're moving in three planes. So which means we divide the pressure by 3, right? So we have to introduce the third. That's when we introduce the third Nm C squared over L cubed, right? So, but L cubed, we know that L cubed side times side is volume, right? It gives us the volume. So therefore P is equal to third, right? So it's third Nm C squared over V, right? So now, so that's the equation, right? Or we can also say if V goes there, we can also express in this form: PV is equal to third Nm C squared. So PV is equal to third Nm C squared, right? So that's another form. Okay, so then this is, let's say 1, then we label this 2, right? So do you see it? But from equation 1, right? Nm over V. So what is mass over volume? So mass over volume, we know that mass over volume is density, right? So it's rho. So which means we can also express this equation as P is equal to third, right? Is equal to third rho C squared. So we can also express it this way: third rho C squared, right? So that's another way of expressing this equation, right? So now I want to look at the relationship between temperature and kinetic energy, right? So let's look at using that equation, right? Okay, so just a recap. Let me just do a recap. So we're considering a molecule. First of all, to consider a molecule, right, that is rebounding with this shaded face, right, elastically. So the change in momentum will be equal to mc minus, since it when it rebounds, it travels in the opposite direction, it's minus mc. So it's mc plus mc, which gives us 2mc, right? So that's the change in momentum. Then the time between collisions. If it rebounds here, so the molecule ikarovera paface iri shaded, handidini yobva yadzokera yofamba distance L and yonoroverawo iri face risiri shaded iri, yobva yadzoka futi yorovera futi pathis face kechi2. So inenge yatravela distance of L plus L kuenda L nekudzoka futi L. So that's the distance. So the time between collisions is 2L over C, the speed that it is traveling at. So the speed yanenge ifamba nayo is what? It's C. C is not necessarily speed of light, it's just the speed of the ideal gas, right? And then according to Newton's second law, right, so the force is equal to the rate of change of momentum, right? So 2mc divided by time, which is 2L over C. That's when we have F is equal to mc squared over L, right? So the pressure now is force over area. So it's mc squared over L divided by area, it's L squared. So we have pressure is equal to mc squared over L cubed, right? So that's how we do it. And then we introduce N for the number of molecules in the gas, right? And then the third for three-dimensional motion, right, in the XYZ plane. And then L cubed is volume. We know that. Okay, so now I want to look at temperature. So I want to look at temperature and kinetic energy, right? Temperature, temperature and molecular kinetic energy. Temperature and molecular EK. So temperature and molecular kinetic energy. All right. So we have our equation. Remember the ideal gas equation. PV is equal to nRT, right? The ideal gas equation we deduced earlier, right? And also we have this equation. Remember, we have this equation 2 here, this equation 2 here. So which says PV is equal to third Nm C squared, right? So we can say third Nm C squared is equal to nRT, right? So want to deduce an expression for kinetic energy, right? So which means if we say m, right, mc squared is equal to 3 nRT over n, sorry. So over n, right? This exactly. Okay, and then we say we know that n. All right, let me take you back to chemistry a bit. So we know that number of moles, right? We can write here. Okay, so let me just write on the top here. So we know that number of moles is equal to number of particles over Avogadro, right? Number of particles over Avogadro, right? So which means Avogadro's constant is equal to number of particles over number of moles, right? So over number of moles, which means 1 over Avogadro is equal to n over number of moles over number of particles, right? So which means when we have number of moles over number of particles, we just replace 1 over Avogadro here. So we have mc squared is equal to 3 RT over Na over the Avogadro's constant, right? And then we know that, but, right, R over Na is equal to K, which is called the Boltzmann constant, right? So which is called the Boltzmann constant. So we have mc squared is equal to 3 kT. So mc squared is equal to 3 kT, right? So, and then we divide everything by half, right? So we have half, right? Everything by 2. So we have half mc squared is equal to 3 over 2 kT. So half mc squared is equal to 3 over 2 kT. So this means, right, kinetic energy, of which half mc squared is the average kinetic energy of the molecules in a gas. So it means kinetic energy is equal to 3 over 2 kT, right? 3 over 2 kT. So from this relationship, we can deduce that the kinetic energy, right? We can see the kinetic energy, right, is proportional to the thermodynamic temperature, right? So it says the mean translational kinetic energy, right, of an ideal gas is proportional to the thermodynamic temperature. So this is evidenced by this formula. EK is proportional to T, right? So the mean translational kinetic energy of an ideal gas is proportional to the thermodynamic temperature. So that's how you We deduce that. So which means if we increase the temperature of an ideal gas, we're increasing the kinetic energy. We're increasing the kinetic energy of the gas, right? So the Boltzmann constant, it's in the booklet, right? It's 1.38 times 10 to the power negative 23. You'll be provided with the Boltzmann constant. Right? So that's how you deduce the formula, right? So that's how you deduce the formula for the relationship between pressure and speed, and then kinetic energy and thermodynamic temperature, right? Okay, so now want to take a look at thermodynamics of an ideal gas, right? So want to take a look at thermodynamics of an ideal gas, thermodynamics of an ideal gas, right? So thermodynamics of an ideal gas, right? All right. So remember your first law of thermodynamics, right? So the first law of thermodynamics, right? We know that the first law of thermodynamics, change in U, right? An increase in the internal energy of a gas is equal to the sum of the thermal energy added to the system plus the work done on it, right? So that's the statement for the first law of thermodynamics, right? So the internal energy of an ideal gas, we talked about the internal energy of an ideal gas, so it's due to what? Okay, so the internal energy of an ideal gas is due to, so we know that the internal energy of an ideal gas is due to the EK trans translational kinetic energy, only because an ideal gas is negligible potential energy. You said there are negligible intermolecular forces between the gas. It's an ideal gas, right? Remember the assumptions. Okay, so the total, which means the total kinetic energy, we deduce the total kinetic energy, right? We said EK is equal to 3 over 2 kT. So the total kinetic energy is proportional to the what? To the thermodynamic temperature. So to change the temperature of an ideal gas, right? To change the temperature of an ideal gas, either the gas has to do work, right? Or we have to do work on the gas, right? So work has to be done by the gas, or we have to do work on the gas, right? So we said to change the temperature of an ideal gas, right? So the gas, so we say work has to be done by on or by the gas, right? So that's simple. Work. So we know that work has to be done on or by the gas, right? So it's, work has to be done on or by the gas, right? So if work is done by the gas and the temperature decreases, right? So which means energy leaves the system. If a gas does work, energy leaves the system, right? If work is done on the gas, we explained, if we compress a gas, right, it increases temperature. We have done work on the gas, right? So the internal energy increases. That's why we say the temperature increases, right? So work is done when a gas changes volume, right? So work is done on a gas when its volume changes. When its volume, right? Work is done on a gas when its volume, right, is reduced. Okay, yes. When its volume is reduced. Okay. So when its volume, so we do work on a gas when its volume reduced, right? So when a gas expands, when a gas expands, so we know that when a gas expands, we're doing work on the gas, and so the gas is doing work. So when a gas expands, right, the work done by the gas done by the gas W is equal to P times change in V. So it's pressure times change in volume, right? So the work done by the gas is pressure times the change in volume, right? So for a PV graph, right? So for the PV graph, right? Pressure volume graph, be for the pressure volume graph, right? So the work done by the gas is given by the area. So it's given by the area under the graph, by the area under the graph. So it's given by the area under the graph. So work done by the graph, by the gas is given by the area under the graph, under the PV graph, right? Okay. So example, so we're considering this example. So we have this example. So pressure in pascals, right? And then we have volume V in cubic centimeters, volume V in cubic centimeters, right? So and then we have okay, so the volume decreasing, right? And then we have here. So these are strips, right? So if you want this, let's say you want so this is V1, right? And then this is let's say this is V2, right? And then we have P, right? Okay. So the total work done when the volume changes from V1 to V2 equals to the total area under the graph, right? From V1 to V2, right? So which means so we say the total work done, let me just change that. Okay. So we're saying the total work done, right? So the total work done from V1 to V2, right? Work done is equal to pressure, right? Pressure times V2 minus V1. So it's pressure times change in volume. So it's pressure times change in volume. Was we were at here? Okay. So that's how the thermodynamics of an ideal gas, right, guys? So that's the thermodynamics of an ideal gas. And we've come to the end of the lesson, or is the conclusion of the topic ideal gases, right? So it's the conclusion of the topic ideal gas. So the next topic is transfer of thermal energy. Yes, so it's transfer of thermal energy. That's the next topic. Thank you.